Okay, then. Good morning and welcome everyone to this lecture, lecture number 28 on work, power, and energy. Basically, right now we are not dealing with work, power, and energy. We are dealing with circular motion. And if I remember correctly, in the last class we had dealt with the first two terms that we encounter in circular motion, and the first two terms were. Anyone can tell me what did we discuss in the last class? We were discussing circular motion. That is what I remember. What were we discussing? Which particular topic we were discussing? Vahini? Angular position. We were discussing angular position and angular displacement, and we had seen that every term in circular motion or rotation comes from the translatory motion part. In that translatory motion or motion in a straight line, we have position vector. Here in case of position vector, we have angular position. There we had displacement, which is a vector, displacement vector, change in position vector. Here we have angular displacement. Those were the two terms that we had discussed. We'll continue on with the same discussion and we'll move on to the next term, and the next term in this category, as everyone can see, there it was velocity. There it was velocity. Here it is angular velocity, denoted by the letter omega. This is the letter omega, Greek alphabet, angular velocity. Now, what is angular velocity? It is the rate of change of angular position, very simply put. Again, as we had as we had seen, that velocity can be described in two ways. It can be average velocity, total displacement divided by total time, or it can be instantaneous velocity, dr by dt. Yes, Vaini. Similarly, we also have two types of, or we can think of angular velocity in two ways. One is known as average angular velocity. How will I write it? I will write it as omega, and I'll put a dabba. This dabba means average. So this average angular velocity is total angular displacement divided by total time. So you can write it as theta 2 minus theta 1, final angular position minus initial angular position divided by total time, or you can write it as delta theta by delta t. Now remember, this delta theta term is a scalar. This is a scalar. Remember, when the angular displacement is more, we treat it is a scalar. We had seen the commutative property. Since delta theta, large change in angular displacement, large change in angular position, is a scalar, and therefore this average angular velocity would also be a scalar quantity. What would be the SI unit for this? The SI unit for this would be radians per sec, rad per sec, radians per second, and the dimensions would be simply t raised to the power of -1. I hope we understand this. It is pretty damn simple. Whatever we have learned in the first chapter, motion in 1D or motion in 2D, same things are going to come here. Only angular word is getting added, angular position, angular displacement, and the third one is angular velocity, average angular velocity. I'll give you a minute so that you can note this down. If the we'll move on to the next term, and the next term is definitely instantaneous angular velocity. The first term was average angular velocity. The second term has to be instantaneous angular velocity. And what is instantaneous angular velocity? It is the angular velocity right now. It is the angular velocity right now. And the angular velocity right now denoted by the letter omega. And this is a vector, and therefore we write the symbol of vector on top of it. Omega vector becomes d theta vector by dt. Remember this d theta, which is a very small change in angular position, is a vector, and hence this instantaneous angular velocity omega vector is also a vector. And remember which type of vector this is. This is an axial vector. I have discussed axial vectors. The direction of these axial vectors are given in terms of axis, and the direction in terms of axis is given by the right hand thumb rule. If it is on positive y-axis, if something is rotating on positive y-axis, you hold the positive y-axis, thumb should point in the positive y-axis of your right hand, and this is how it will turn. Instantaneous angular velocity d theta vector by dt. Average angular velocity, Harshita, is delta theta by delta t. You must be smart enough to write it when the time is given to you. I'll wait for a minute for everyone to note instantaneous angular velocity. The time starts now. Note it, Harshita. Average angular velocity is total angular displacement, delta theta by delta t. Note it down. So, I think you have noted it down. Let us move ahead and see what is next. Now, what would happen? What would happen if your angular velocity is constant? It does not change. Now, this concept is similar to your velocity being same, a particle moving with uniform velocity. Its motion remains a straight line motion with the same speed. It will continue to keep on moving in the same straight line with the same speed. That is known as uniform motion, or that is known as motion with uniform velocity. It will not change its direction. It will just keep on going forever in the same straight line. Similarly, if you have omega, which is angular velocity, is constant, so I'll just write it as an important note. If omega, angular velocity, is constant, if omega, the angular velocity, is constant, their velocity was constant, the motion was known as uniform motion. Here, angular velocity omega is constant, therefore the motion would be known as, any guesses? What will I call this motion if the angular velocity omega is constant? I will call this motion as, I think rotation is already done in your class, so you must be knowing. You must have gone through circular motion. Yes or no? No? You've not gone through circular motion? Okay. If omega is constant, then what happens? What will I call that motion? If velocity is constant, I call it uniform motion. If omega is constant, what would I call it? Yes, Raju, I will call it as uniform circular motion. I will call it as uniform circular motion. And this uniform circular motion is going to come in many ways, many different ways. Uniform ka U, circular ka C, and motion ka M. And this motion in short becomes UCM, uniform circular motion. The next heading that we'll write will be UCM, uniform circular motion. What is uniform circular motion? So the first point that you must remember is If angular velocity is constant, then the motion is known as uniform circular motion. We have already seen that, not a problem. Now, if omega is constant, constant means it does not change. It does not change in magnitude. It does not also change in direction. When I talk about direction, the axis does not change. That means if it is moving along positive y, if it is rotating along positive y, it will always rotate along positive y. It will also move like this. It will always move like this. It will always move like this. It will also not move like this. It will not even reverse its direction. It will just keep on moving in the same direction along the same axis. I hope you understand this. Can I have some raised hand? Omega is constant. The body will keep on moving along the same axis. Remember, it is not a straight line motion. The body will change its direction, but the axis on which the body is rotating, that axis remains same. So it always turns like this. Only 5 people have understood this. It is so difficult to understand. Again, listen. Omega is constant. It does not change in magnitude. It does not change in axis. If it's rotating along positive y, it will keep on rotating along positive y. One more thing that you must remember, if omega is constant, your instantaneous angular velocity, if I take the magnitude, that will be equal to your average velocity, average angular velocity ka magnitude. Remember why I'm writing magnitude here, because one of them is a scalar, the other one is a vector. So I cannot equate both. Scalar cannot be equal to a vector. This gentleman, the pink gentleman, is a scalar. This gentleman is a scalar. And the other gentleman, the green gentleman, the green Hulk, this green Hulk is a vector. So I just cannot write. So I just cannot write that omega vector is equal to average omega, because one is a scalar and the other one is a vector. Remember, in uniform velocity, go back to uniform velocity. When the velocity is uniform, average velocity and instantaneous velocity both are same, but they are both vectors. So I wrote v vector is equal to v average vector. Both were vectors, so I could equate them. Here I cannot equate them because one is a vector and the other one is a scalar. What I am equating here right now is their magnitudes. Do we understand this? Can I have some raised hand that we understand this? That is why I've written it in terms of magnitude. I'll give you 2 minutes to note whatever is taught up till now about UCM. I'll give you 2 minutes. I hope everyone notes it down. I hope all of you have noted this down. The important points about uniform circular motion. We have discussed 2 points. Let us now move on to the third point. Now, if the angular velocity omega is constant, the body will complete one revolution. Instead of calling it one revolution, we can call it one rotation or one complete chakkar or one circle, if you call it circle. So if the angular velocity omega is constant, it will complete one revolution, one rotation, or one circle in a fixed time. The time will remain fixed. Yes or no? Do we understand this? If it is completing one revolution with uniform velocity, it will always do it in a fixed time. That fixed time is known as, anyone can tell me? That fixed time is known as? That fixed time is known as the time period of uniform circular motion. That is known as the time period of uniform circular motion. So that is the next thing that we will write. Time period of uniform circular motion. Time period of uniform circular motion denoted by the letter capital T. It is the time taken. It is the time taken to complete one revolution or one rotation. It is the time taken to complete one revolution or one rotation. For uniform circular motion, this time period, time taken to complete one rotation, would be fixed, and therefore this term is normally only used with uniform circular motion. You can make a question where the velocity is not uniform, and then you are asked how much time it will take to complete one rotation. That question can also be done, but then normally we don't call that time as time period. We can call it, because that time period will continuously keep on changing. So basically, in practical language, we use time period for uniform circular motion, time taken to complete one rotation or one revolution. Now you can take some real life examples for this. For example, you have seen uniform circular motion in your daily life. Can anyone tell me some examples of uniform circular motion, and can you tell me what is the time period of those uniform circular motions? Anyone? Yes, the clock. The motion of a clock is uniform circular motion. In fact, the better way to say this would be the motion of the hour hand, minute hand, and the second hand are uniform circular motion. The second hand, the hands which shows you the second, it completes one revolution in 1 minute, one revolution in 1 minute from 12 to 12. Therefore, its time period becomes 1 minute. For the minute hand, the time period is 1 hour. For the hour hand, the time period is 12 hours. And yes, motion of Earth around the sun, 365 days, uniform circular motion. Motion of Earth on its own axis, 24 hours, uniform circular motion. And you also know the time period. Simple things, and I hope you are able to understand this. T stands for the time period. The SI unit for time period is time. So SI unit is seconds. No questions asked, no answers given. That is point number 3. Now we move on to point number 4. Now when you have time period for a uniform circular motion, you can also find out how many revolutions it takes in 1 second. How many revolution it takes in 1 second, and that is known as the frequency of uniform circular motion. So what is frequency of uniform circular motion? It is number of revolutions or rotations in 1 second. Remember, it is not 1 minute, it is not 1 hour, it is not 1 day, it is 1 second. The SI unit for this thing is hertz. The SI unit is hertz, and remember, 1 hertz is 1 revolution per second. 1 revolution or 1 rotation per second, and the dimension becomes 1 by t, or t raised to the power minus 1. Do we all understand this? Can I have some raised hand that we understand this? The frequency is normally denoted by the letter, small letter f. Just like friction, we also denote frequency by the small letter f. Only 5 people have understood this. This is not good. That means something is wrong somewhere, and I'm not doing a good job, or everyone else is on a sleep mode. And I've also told you everywhere, every time, that if you think that being in the class and listening to whatever my babbling, if that thing is going to clear the JE for you, you are mistaken. This is not Hogwarts, and I am not Dumbledore. I don't have a magic wand, and I wave that magic wand and I create Hermione's and Harry Potter's out of you. You're not Harry Potter's, not Hermione's, and I'm not Dumbledore. And this is not Hogwarts, right? So you have to work harder. Even Harry Potter and Hermione's had to work harder. Nothing. They did not become wizards for free. They had to work. Just attending a class will not help you a lot. You will have to put in some effort. Frequency, number of revolution in 1 second. SI unit is hertz, 1/second. I hope everybody has noted it down. I'll give you a minute still to note it down and come at pace. But I hope you have noted it down. Simple things, not so much complicated. Now, there's a relation between omega, the angular velocity, t, time period, and f, frequency. And I guess most of you would be knowing it, but still, what is the relation? These are the important formula that you must remember. T, time period is 1/f, or f is 1/t. Doesn't matter how you write it, it remains the same thing. Omega, angular velocity, which is constant, is 2 pi by t, or you can also write it 2 pi multiplied by f. I hope everyone understands this formula. Now, remember, these formulae are only valid for uniform circular motion. It's not valid for non-uniform circular motion. Here, angular velocity omega is constant, and therefore you have time period and frequency, which are also constant. If omega changes, time period and frequency will keep on changing, and hence these terms will not have much meaning. I hope you understand this. Here, one more thing you have to understand, because we will be using this thing not in this chapter, but in the coming chapter, maybe in SHM, definitely in SHM, and also in alternating current AC, which is in 12 standard. Omega, up till now, whenever you are dealing with uniform circular motion or rotation, normally we say omega as angular velocity. Omega is angular velocity. No doubt on that. Omega is angular velocity, but we can also call it by a different name. Omega can be, see, some of you would have a name which is used at your home. Your mommy, dad use that name. Then there is one name which is used by your colleagues, your batchmates, your friends. You might also have nicknames, funny nicknames. In my college, we had funny nicknames. One of the friends of mine was known as Bhai. One of the friends was known as TG, and they were different names. And there are some names which I can't even tell you. But yeah, everyone has at least one or two names normally. My ghar ka naam, and which my father gave me, was Nikki. It sounds like a girlish name, but yeah, it is that. Outside name is Astik, and I have a lot of nicknames throughout my school life as well as my college life. On similar lines, omega, which is angular velocity, you can call angular velocity the official name. It also has a nickname. You can also call omega in a different way. Now, what is that different way in which you can call omega? See, this F. This F is definitely frequency. This F is definitely frequency. No doubts, no questions asked, no answers given. This F is definitely frequency. And if I just put this blue color on this 2 pi, this 2 pi is definitely angle. This 2 pi is the angle in radians which a body covers in one revolution. In one revolution, in one rotation, if the body is moving on a circular path, or any path, even it may not be circular, it may be a closed path, it will travel an angle of 2 pi, which is 360 degrees. Yes or no? So this 2 pi is basically angle in radians. Now, omega is angular velocity, yes, but it can also be called by a different name. See, now I can formulate that name. Angle, oops, wrong color, green. No, let me use yellow. Angle and frequency. I can combine these two terms together, and I can have a new name for angular velocity with the combination of angle and frequency. I can also call this omega as, anyone? Any guesses? It is definitely angular velocity. No questions asked, no answers given. But I can combine with angle and frequency, and I can call this omega as, anyone? Any guesses? No one? Angle and frequency combined together, and I can call this omega as angular frequency. So you can also use this term for angular velocity. Normally it is not used in rotation wala chapter or circular motion wala chapter, but we would be using this angular velocity in angular frequency in simple harmonic motion. In simple harmonic motion, you will also have angular velocity and you will also have angular frequency at that point in time. Don't get confused, because you will be having both of these terms coming to you, angular velocity as well as angular frequency. I hope you all understand this. Can I have some raise hand that you understand the formulae and the other name of angular velocity? I'll give you a minute to note it down. I hope you can note it down faster. Well, I hope you have noted this down. Relation between T, F, and omega, and why omega is can also be called as angular frequency. We move on and move on to the next thing. What could be the next thing? Up till now, the angular velocity was constant. No one was changing it, neither in the magnitude nor in direction. And when I talk about direction, I talk about the axis of rotation or axis on which the circular motion is performed. What can change angular velocity? This question is same as how do you change velocity of a moving body? To change the velocity of moving body, we have to accelerate it. Acceleration is the change or the rate of change in velocity. Similarly, if you have to change angular velocity, what would you need to answer? If I have to change angular velocity, what do I need? Whatever terms we have read in that chapter, chapter number 1, the same terms are coming here. Only word angular is added. To change velocity, I need acceleration. What do I need to change the angular velocity? That is the question. It's a simple, straightforward question. What would be the simple, straightforward answer for this straightforward question? How do I change angular velocity? No one? Is anyone there in the class? I hope I am audible and visible and everyone can hear me. Yes, Santosh, that is correct. To change angular velocity, I need acceleration, and I would call that acceleration as angular acceleration. That is the next heading that we are going to see. Angular acceleration denoted by the legendary letter alpha, which is a Greek letter. Again, if you go back to the first chapter, we can define this in two different ways. One is average angular acceleration. So I have alpha, and this is a vector. So I put a vector sign, and then I also put a dabba. Dabba means it is average. It is nothing but equal to total change in angular velocity divided by total time. So it simply becomes delta W. Oh, it's not W. Delta omega by delta T, total change in angular velocity divided by total time. It is a vector. It is an actual vector. The SI unit is rad per sec square, radians per second square, and the dimension is t raised to the power minus 2. No questions asked, no answers given. It is pretty straightforward. Similarly, if you have average angular acceleration, you must have an instantaneous value which is known as instantaneous angular acceleration. Alpha vector, one is alpha vector dabba, the other one is alpha vector. And this alpha vector is instantaneous angular acceleration, is the acceleration, angular acceleration at this point in time. d omega vector by dt. The SI unit is rate per sec square. The dimension is definitely t raised to the power minus 2. I will give you a minute to note both of these things down. If you have any doubt, you can always come up to me. Simple things. We have already discussed it. 1 minute, 2 minutes to note these things down. Well, I hope everyone has noted this down. Let us move ahead and see what is next. We have seen angular acceleration. It could be of it could be thought of as two types of angular acceleration: average angular acceleration and instantaneous angular acceleration. Now, the next thing that you must understand, if the angular acceleration alpha is constant, so it does not change. Now, if angular velocity is constant, the motion becomes uniform circular motion. If angular acceleration is constant, then the motion will be known as it is same as what we had seen in the first chapter, motion with constant acceleration. Remember, motion with constant acceleration. Here I will call it circular motion with constant angular acceleration. Circular motion CM with constant angular acceleration. So this is same as motion with constant acceleration. This is circular motion with constant angular acceleration. And if angular acceleration is constant, that would mean alpha vector, which is instantaneous angular acceleration, that will be equal to alpha vector with a dabba. That means instantaneous value of angular acceleration and average value of angular acceleration would all be same. Do we understand this? Can I have some raised hand that we understand this? Yes, sir. It's very simple. If alpha is constant, if alpha does not change, both the values wherever I take it will always remain same. Please note this down so that I can move further onto this topic. I hope everyone has noted this down. Circular motion with constant angular acceleration will remain constant. Now, when angular acceleration remains constant, this motion is similar. The equations are similar. The motion is not similar because this is moving in a circular path. Previously, it was moving in a straight line. So it's not exactly same, but the concepts are similar. This is conceptually similar to motion with constant acceleration. Motion with constant acceleration. And in that motion with constant acceleration, we had equations of motion. We had equations of motion. Similarly, here we also have equations of motion for constant angular acceleration. And that is the next heading that you are going to write. Motion with constant angular acceleration. Motion with constant angular acceleration. This is same as motion with constant acceleration. The formulas are similar. There we had V, final velocity. Here we have omega as final velocity. You can call it omega 2 as well. There you had U as initial angular velocity. Here you have omega naught as initial angular velocity. Sorry. Omega as final angular velocity. There you had A as acceleration. Here you have alpha as the constant angular acceleration. There you had delta R, delta R, delta R or S as your displacement. Here you have delta theta, change in angular position, as your angular displacement. And now you can write the equations of motion for constant angular acceleration. No prizes for guessing this one correct. The first equation is there. I will write it here. The first equation was V is equal to U plus AT. So it's a revision of your first chapter. Here it is. Final angular velocity omega is equal to omega naught plus alpha t. I hope everyone understands this. The second equation here is delta theta, which is angular displacement. Delta theta is omega naught t plus half alpha t square. There it was delta r will be equal to ut plus half at square. Everything looking same. No prizes for guessing this one right. The third equation there was, the third equation here is omega square is equal to omega naught square plus 2 times alpha into delta theta. Or don't write it theta because theta is angular position. Delta theta is change in angular position, which is your angular displacement. There, if you go back, the equation was v square is equal to u square plus 2 times a into delta r. But remember, whether you are dealing in circular motion or you were dealing in motion in a straight line, both wherever you have vectors dealing with it. So here you had a sign convention. Here you had a sign convention which is written in blue. The sign convention was, if it is positive x-axis, it is positive. It is, if it is negative x-axis, it is negative. If it is positive y-axis, it is positive. If it is negative y-axis, it is negative. We use, instead of vectors, we use signs: positive, negative, positive, negative. Do we all remember this? Can I have some raised hand? Yes, sir, we remember this. The sign convention for your normal equation v is equal to u plus at. Remember, these equations are only valid for constant angular or constant acceleration. Do we remember this? Yes or no? Can I have some raised hands? I'm not having raised hands. Can I have some raised hands? Only 14 people seem to have understood this. That is not good enough. Let me call everyone who is sleeping. Venkatesh, Ashwan, Thanos, who is this? Thanos double X. Vijay, Venkatesh, Harshita, Satvika, Sai, Kushi, Padmakant, Sainath, Krishna, Kartik, Shashank, Kevin, Jagdish, Jyotsna, Tejasvi, Deepak, Charita. Are we there in the class? Or is the mobile phone on and we are having a gala time somewhere else? Okay. There we had a sign convention. Here I will just mark it by red. Here also we have a sign convention, and I think that I had discussed that sign convention yesterday. Can anyone remind me of what is the sign convention for this circular motion? Can anyone tell me what is the sign convention for this circular motion? Anyone? What is the sign convention? Because here also right hand thumb rule. Okay, Chatur, right hand thumb rule I understand, but what do we get from that right hand thumb rule? Clockwise, anti-clockwise. Things are going to rotate only on one axis. They are not going to rotate on x-axis, y-axis, and z-axis altogether. They will only rotate on either x or y or z. What is the sign convention? Anyone? Right hand thumb rule is correct, but what can we get from that right hand thumb rule? It seems that no one has followed the last class, so I will request all of you, to have a look at the last lecture where we had discussed the sign convention as well as the first two terms. So if you take that class and you put this class together, your circular motion would be covered. The sign convention for this was pretty simple. Anti-clockwise, if it is moving like this, anti-clockwise was taken as positive, is taken as positive, because anti-clockwise means it is on positive z-axis. clockwise. If something is rotating clockwise like this, it is taken as negative. If you remember the very first day when we were discussing about angles, I told you if the angle is anti-clockwise, the angle is positive. If the angle is clockwise, the angle is negative. This is what we will use here. Anti-clockwise as positive, clockwise as negative. This is the sign convention for the red one, which is for the circular motion. The blue one is the sign convention for your normal motion. I'll give you 2 minutes to note this down. If you have any doubts, please ask. These are the three equations, equation number 1, equation number 2, equation number 3. I'll give you one more equation and then we will wind up this class. 2 minutes for everyone to note it down. Well, I hope everyone has noted this down. Now, before moving on with this class, there is one last thing that you must remember. The fourth formula. And to understand this fourth formula, I'll give you the fourth formula here. The fourth formula for both these cases, for the red one, which is angular velocity, the fourth formula is average angular velocity will be equal to omega plus omega naught by 2. Now, this fourth formula is exactly similar to what we had seen for average velocity. Average velocity is v plus u divided by 2. Do we all understand this? Can I have some raise hand that we understand this, sir? If the acceleration is constant, you can find out average velocity as v plus u by 2. That was the formula that I had given to you. Similarly, if angular acceleration is constant, I can call average angular velocity as omega plus omega naught by 2. Can I have some raise hand that we understand this? So this is equation number 4. Anyone understands this? A raise hand will give me more confidence. Then we have the fifth formula, which is angular displacement would be equal to average angular velocity multiplied by time. Average angular velocity is omega plus omega naught by 2 divided by time. The formula on this side would be delta r. Displacement is v plus u by 2 multiplied by t. This would be the equation number 5. Equation number 5 for normal motion. Equation number 4 and equation number 5 are here. Then we have the last equation, which is the displacement in the nth second. Here it is angular displacement in the nth second. This is equation number 6. Omega plus alpha by 2 into Tn minus 1. Okay. Do we understand this? Do we remember this formula? Anyone remembers this formula for the nth displacement in the nth second? Anyone remembers this formula for displacement in the nth second? Okay, what we'll do is we will see this formula in the next class. We'll again, okay, why do you remember this? Great. How did you get this? Any idea? Okay, we will get back to this formula. I will give you time to remember this formula and tell me what is the sixth formula here for displacement in the nth second. That is your homework. Tell me what is the formula for displacement in the nth second and find out the formula for angular displacement in the nth second. That is the task for tomorrow. I'll just rub this off. That is the task for the next class. Tell me what is the formula for displacement in the nth second and angular displacement in the nth second. With this, I will wind off today's class. In today's class, we have seen the basic things about circular motion. We'll continue with the same thing. in the next class that will be on Monday. Till that time, take care, stay at home, stay safe, get vaccinated. We'll see you in the next class. If you have any doubts, please ask. Else, the class is a wrap from my end. Enjoy your day.